Thanks very much, guys. It's very exciting to be here and come out to Berkeley and tell you guys a bit about what I've been up to lately in this field. So yes, I'm going to tell you guys a bit today about, we've been looking lately for naturally caused radio emission from specifically directly imaged exoplanets. So we have some future plans as well. This is all mainly with the Very Large Array in New Mexico. So, tell you guys about this sort of work, what we've been up to and where the field is going. But yes, so the intro was correct. I did actually start my radio astronomy career. I was in 2008 an undergrad RU student at the SETI Institute, and I was working on the Allen Telescope Array with Jill Tarter, which in 2008 was still a Berkeley project. So I was told that if I showed some pictures from that, which let's see if I am allowed to progress in my slides. Yes, this would be appreciated by some of the SETI or the people here. So the Allen Telescope Array, I mean, it was California. So of course there was a giant forest fire in 2008. So we had a lot of very pretty orange pictures. As I said, my career was looking for RFI with the Allen Telescope Array. We found like a ton of harmonics from the control room. And there was this weird like little RFI detector thing that was there at the time. This was Billy, I don't remember his last name. He was one of the telescope operators at the time. So searching RFI. This was the control room at the time.
I didn't recognize him. He looked so young.
Does Garrett apparently?
Garrett,
yeah. I don't remember anybody's last names, but I did find the first names. So yes, I guess my radio astronomy career did start in this area. So it's very nice to be back, and I'm excited to catch up with Jill later today at the dinner and things like that. And I should also say I was told that my husband, who's not an astronomer, did SETI at home until the very end. And we had like a little computing cluster in our house. So, donated some electricity time to this project and all that good stuff. So, very excited to be here. But so what I wanted to tell you guys a bit is what I've been up to since 2008. So first of all, this is going to be about natural exoplanet emission, not the other kind. So, why are we interested in this as a field? So basically, if you're looking at the detection of radio emission from exoplanets, that's basically related to the magnetic field surrounding these exoplanets. And there's been a lot of interest lately in finding this now that the telescope sensitivities are really getting to the point where this is possible. And it would really open up a huge new research field with a lot of different areas for exoplanet studies. So what you could be, you could look at the interiors, for example, the interior structure of exoplanets. Currently, very little is known about them. You can look at things like atmospheric escape. Of course, if you have a magnetosphere surrounding your planet, you're not going to have the atmosphere stripped off quite as quickly. Things like star-planet interactions. A lot of this depends on particles, like for aurorae are created from particles from the sun, similar things. And of course, habitability, because we think that if you have a magnetic field surrounding the exoplanet, that is better for any potential life forms on it. So first, I'm going to give an overview of what we know about radio emission from planets in general. And these are all the detected confirmed planets that have radio emission so far. And of course, they're all the planets in our solar system. But it should be noted that all planets in our solar system that have a magnetic field will emit natural radio emission on some level. So that's pretty interesting. It's geosynchrotron radiation is what we're looking for. So this is just electrons spiraling in magnetic fields, all this sort of thing. So if we look here, x-axis is the frequency here in kilohertz, normalized flux density. So it's not quite Jansky's, it's like a little bit different. You can see that all the planets, do have some sort of level. Some are, of course, much brighter than others. The other thing here, very important to keep in mind, is of course, below about 10 megahertz, you start basically being blocked by the atmosphere. So on this plot here, what you can see, everything to the left here has only really been studied from space. Everything on the right here is possible to be observed from the ground. So if we're looking at this plot here, Uranus and Neptune are the faintest, and those are basically only from Voyager 2. We have that data. We don't really have any other data on the magnetic fields from those planets. Of course, they're very faint. Of course, the Earth, we know very well because, we hang out here a lot. Saturn and Jupiter, of course, have had many more probes traveling to them and things like that. So that's been a bit of a bigger area of study. And then, of course, we have different kinds of peaks to the emission if you're looking at the lowest frequencies to the highest frequencies. And the one that most people are interested in, just because it is the easiest to study, is what is called Io deximetric. So talking about the size of the length of the waves emission coming from Jupiter. So we're going to talk about this a little bit in more detail. just because there has been a lot of research in this area lately looking for this specific type of emission. We're going to be talking about the type of emission I'm looking at later. It's a different kind, but just so we're all on the same page here. So radio emission from Jupiter, it is basically the brightest radio source in the sky if what the radio maser that is created is pointing at Earth. So it's a very bright radio source. It is basically created by the Io has its volcanic moon. These particles go into its magnetosphere and then it creates this radio maser, as I said. This is what Jupiter looks like in the radio at the lowest frequencies that I was talking about. Looks like a giant space lizard. This is roughly where Jupiter is, and then that's much, much larger in both directions compared to the size of Jupiter itself. It is important to note that this emission, as it currently is, it is not going to be detectable outside of our solar system. But then, of course, it's always a proof of concept type thing where could we scale this up, maybe detect this around other exoplanets. So for example, if Jupiter was much closer and the sun was much younger, so much higher UV, you would have more particles. Something like that maybe could create something that you could detect further out. And the final thing to note that's very important in a lot of these studies when we're talking about this, there's a very steep cutoff at about 30 megahertz when you're talking about emission from Jupiter. And also that it's highly circularly polarized. This is a way you can tell the Jupiter emission or potential planetary emission versus other things. Though of course, everything is somewhat polarized if you get down to it, just a bit more than others. So in order to basically detect this type of emission at higher frequencies, if you're assuming that, you basically just have to have it be much higher to begin with. And then the cutoff, you know, if it was 1,000 times brighter, you would have a cutoff that you could still maybe detect this at higher frequencies. So to go on though, one thing I also just wanted to check, I mean, radio astronomers, normally when I'm giving this talk, and if it's just to exoplanet people that don't know anything about radios, you can have to explain radio telescopes, so we don't have to spend much time on this. But it is important to note also for everything that's going to be talked about for this potential emission, the VLA versus LOFAR, and they're very different instruments. And these are kind of the two telescopes right now being used for a lot of this natural radio exoplanet studies. So, you know, this is the VLA on the left, our 27 antennas. A configuration, the important thing for my research to note is it gives you sub-arcsecond resolution. So 0.3 arcseconds roughly at about 6 gigahertz, where it is the most sensitive. And you can get down to 1 microJansky in sensitivity at 6 gigahertz. So it's effectively the most sensitive radio telescope. So I realize things like Meerkat are, you know, hopefully giving us a run for our money soon on this. And then LOFAR, though, is on the other hand, it's a software telescope, does not have the traditional pretty antennas and things like that. It is primarily in a field in the Netherlands. It has outrigger stations further out across Europe. And the important thing to note, though, is that it is a megahertz radio telescope, does not really do gigahertz. I guess the VLA, you can technically do megahertz, just it's not really worth your trouble usually. So
V-Light is there, and it's a
yeah,
constant
V-Light is
light.
great. Yeah, but whenever I've tried to look at V-Light, I've never gotten good limits out of that data, unfortunately.
But we're
So-
hoping, we're working with V-Light to give them a better data processing.
Oh, that would be cool.
It's kind
Yeah.
of an offshoot of another project.
Okay, cool.
Is V-Light operational on all antennas or like 16? or-
It's basically as long as you don't specify P yourself in your observation, you just get everything in light, like all the antennas have a little extra horn on
Yeah,
there.
it's not currently all, I forget what the number
I
is,
think it
but
was 16.
Yeah.
something like that.
Yeah.
They're planning to get to all of them.
Yeah, that's because we were doing some TDE stuff and that signal migrates to lower frequencies as it goes on. So I was like, how does it look? And it was like, not unfortunately that useful. But anyway, so back to this. The important thing to also note for LOFAR is it has a low band and a high band. So low band is below 70, 80 megahertz roughly. High band is above 120 to 160 megahertz. The FM band, of course, is in the middle, and you don't really want to deal with that. And the resolution of LOFAR is also nowhere near what you can get with the VLA. Is also the reason I'm talking about this is because if you've been talking about naturally caused radio emission lately, there's been a few other articles in the news, so I kind of just wanted to go over and contrast the various things that have been discovered so far in this field. So the first kind of Jupiter type emission from exoplanets that I think was very interesting was there was some recent emission from Tau Booties, I think was the particular system there, was detected with LOFAR that might indicate that there was created by an exoplanet. So this is beamformed data at 15 megahertz, so very low frequency with the LOFAR, about as low as it gets. Basically, you're looking for this Io Jupiter type emission, iodam radiation. And it was an 890 microJansky flare. which would basically, as I said, be similar to solar system analogs. Here's, what the flare looked like. The way they kind of said, okay, this flare I think is from this source instead of, just being some weird RFIs. They have 2 other beams on the sky while data was being taken, and you don't see the flare in those. The trick though is, and I started my PhD thesis, I was working on LOFAR and looking for radio transients, and I know full well I have a chapter in my thesis about RFI, which I guess is a continuation of my SETI work now that I think about it. But yeah, there's a lot of weird RFI in the Netherlands, and it's also all not just as easy as, oh, you see it in 3 versus there's a lot of directional stuff as well, things like that. So this really needs more follow-up to confirm if it's genuine or if it's RFI. But it was a very interesting signal. It would be consistent with something from, so Jupiter is about 4 Gauss. This was, I think, about 70 Gauss, they said. So it's like, okay, that would be kind of sensible. And they said that this somewhat correlated with the rotation rate from the planet. So, there are a lot of interesting things about that, but I think it's still something that, really needs to stand up to scrutiny. And then just last month, though, there's another group looking for exoplanets with LOFAR. And they have been reporting several flares at much higher frequencies, 144 megahertz, basically in LOFAR survey data. So your all sky survey type stuff. And this is, the imaging kind. So this is the rest of the talk is going to be more about imaging data than beamform data. But, you can kind of see, okay, there's these M dwarfs and they appear to be flaring. And that's kind of what this report was about. They reported, dozens of these, and they said some of them were from the exoplanets and some were from the stars themselves. And they said, oh, maybe M dwarfs even have aurorae, and that's what's creating that. So also possibly from exoplanets, like there is a lot of interesting details here. I will point out though, one of the big problems is, and also from the previous one, I forgot to mention, you have 5 arcsecond resolution. It's even worse in low LBA mode for LOFAR. So you can't really tell, oh, is this emission from an exoplanet or from the star itself? So one of the papers that came out on this, so I think it was the first, so then plus et al. 2020, they detected an exoplanet around one of these flaring stars. And they also said, based off of our flaring emission, we predict it's going to be between this radius in AU from its parent star. So then the optical people went to go look and they're like, we can rule out an exoplanet there. So it's like, okay. So this is still a pretty difficult field. So like, they're not necessarily targeting known systems. They're basically just saying we see these flaring stars. Also, like there's also just not a lot known about flare stars at these lower frequencies. So how common is this emission, things like that. My understanding from talking to M dwarf people in optical, they're like, yeah, there's just a lot going on. It's nice that people are finally interested in it because we might be able to figure it out. But the connection between this emission and exoplanets beyond just, of course, there's probably exoplanets there. It's a very difficult problem. Yeah.
So you mentioned about the polarization is one of the key ways by which you can distinguish. Was that possible to do it here?
Yeah, so this is a lot of it is, so this is actually, sorry, I forgot to mention, this is the polarization. So I think this is the Stokes V data there. So they're saying we have a very significant percentage of our emission is from polarization.
Oh, okay.
So that's what a lot of this argument is for. And basically we don't, at higher frequencies, we don't see much evidence of polarization compared to what they're seeing at these lower frequencies. So that's why they're even like, maybe M dwarfs have aurora. That was kind of the big interesting result presented in this paper. But yeah, as I said, it's, the first time you do anything, I'm sure you guys know, it's kind of difficult. So I think it's very interesting, and like, we'll see what exactly happens with this. And nothing else, that looks like there might be some new mechanisms for radio emission at these frequencies from these M dwarfs.
So M dwarf is also expected to have similar level of circular polarization as the.
Not necessarily, but I'm going to go into a lot of this is like the theory is not necessarily known for.
Sure.
Yeah, I'm going to talk about brown dwarfs next. So anyway, so this is just kind of a quick overview. I'm also going to say, because like I was talking to like some M dwarf people, and apparently a lot of the research where they were like, they looked at test data, and for example, and they said, oh, these are inactive M dwarfs because we don't see flares in test data that correlates. But apparently you can't do that for reasons I can't recall with test data, like it's not really the right sampling or something like that. And also I think M dwarf people will take offense if you call anything an inactive M dwarf, because that just doesn't exist. So I think that was kind of like, there are multiple things where it's like, these sound like it might just be details, there's, it might be sorted, but it's, as I said, it's just tough, I think. So anyway, so that's kind of the first type of emission. And now I'm going to talk about something different because we're going to move from megahertz up to gigahertz and, stay here for most of the rest of my talk.
And since you're seeing Jill later, you should talk about.
Sorry?
And since you're seeing Jill later, you should talk about brown dwarfs.
Yeah, okay. Yes. Oh, yeah, I didn't think of that. That's true. Yeah. So radio emission from brown dwarfs does not seem to be connected, though, on the other hand, to this emission necessarily. And I'm going to tell you guys a bit about why this is and why this looks kind of independent and why we think it might happen from exoplanets as well. So unlike looking for exoplanets, radio detections of brown dwarfs, there's a much larger, more robust field about it, basically using the VLA and Arecibo. Looking for ultra-cool dwarfs is what we're calling them, so the lowest effective temperature ones at gigahertz frequencies. So I work for, my supervisor is Ido Berger, so he's a big transient type guy. And my understanding, the way he's told me this story, is when he was an undergraduate student in the 90s, he did his RU at the VLA and they gave everybody like an hour of VLA time. And he's like, I want to look at a nearby brown dwarf. And they're like, all right, kid, you're not going to see anything, but have fun. And he detected a flaring brown dwarf, which is this picture here, or this plot. So that was a bit of a shock because nobody was expecting at the time radio emission to be detected from brown dwarfs. And it was also, pretty bright radio emission from this brown dwarf. So that really is what started the field. And since then, people have been looking, and it looks like roughly about 7 to 10% of these ultra cool dwarfs flare. So, we've got the extra complicated problem of you might look one time, not see anything, look again, and you'll see something. And you can also have quiescent emission. Some of these just have underlying low level emission going on. And the real thing here is, like it should be mentioned, we don't fully understand the physics about what is creating this sort of emission. So, and I'll go into a bit about why we think this is separate from that. But basically, as I said, if you had something like a scaled up Jupiter and you're just expecting that emission, you're detecting it at gigahertz frequencies, you need something that's like over a kilogauss in magnetic field strength. So a very, very strong magnetic field. As I said, for comparison, Jupiter's about 4 gauss. So if you were to say, look at this flaring emission, that does look like similar to a 1 kilogauss magnetic field. So, okay, you could think about that. But you also have this quiescent emission that does not necessarily have that. That could be about its tenth as strong. And still you would get this quiescent emission at this frequency. So, there's kind of a lot of questions here. And as a key question though is, does this extend all the way to exoplanets? So we see this in a variety of brown dwarfs. So I'll tell you a bit about that. So for example, if you're looking, there have been recent detections of free floating, roughly 13 Jupiter mass brown dwarfs that have created, you can see radio emissions similar to this from this. So this was Melody Cow et al. Came out a few years ago. So something like, if you look at some of these objects, these are the objects here. So one is like 12.7 plus or minus 1. So it's like, okay, it's really on that threshold. Traditional brown dwarf to exoplanet cutoff is 13 Jupiter masses. Mm-hmm. So the thing to emphasize though is these are all free floating. So they're probably not necessarily formed the exact same way as something that would be a very massive exoplanet around a star. This is probably more similar to just a star that didn't get all the way or something like that. So, but close enough. It's worth thinking about. And the other thing to note though is if you look at these, so if you take the models based off of what we see at low frequencies and project them up to these higher frequencies, what you expect, this is roughly where you expect the magnetic energy densities to be consistent with what we're seeing and everything like that. But the predictions are much, much lower. So if you're taking, a lot of the stuff is based off of Earth, if it's sort of more rocky planet or interior, just because we know the most about Earth. So, but the point is like the predicted emission should be much lower for these objects than what we're seeing compared to what we are seeing. So that's kind of an interesting indicator. The other thing is, so if we look at the submillimeter, so up at ALMA at 100 gigahertz, then you can really kind of get your light curves really well figured out over multiple range of frequencies, not just yellow with the VLA. And I've been working on this a bit with a grad student, a first year grad student, Kevin Ortiz Ceballos. So it's pretty exciting to see this. So there currently have been 2 published ALMA detections of UCDs. So these are basically ones where we know that the emission is pretty quiescent. So just very constant ones. And then, we have 2 more that we just have very standard, well-known nearby quiescent emission. And what we can see is though, if you're following these curves, they're very consistent with just normal synchrotron emission that you expect. There doesn't seem to be any cutoff. If anything, it looks like these are getting brighter over time. So these data points are all currently just archival published observations. And then we have this new data and Kevin just, put it on the plot or added to the plot. So we do have a few observations in the archive with the VLA that we want to grab, just because if anything, it looks like there might be a flattening, but it might also just be that a lot of this data was published, 10, even 20 years ago by now. Maybe these do just change, slowly over time. So we do want to go in and double check to make sure like what exactly is going on with these systems. So that's been kind of interesting. As I said, it doesn't look like there's a cutoff. So it does look like this is something that's going on that's a little bit different than what's going on with low frequencies. And also, I should say, we've been looking, Kevin has been slicing this data in various ways, and it does not look like there's any real hint of variability or bursts or anything like that, at least at all low frequencies up at 100 gigahertz. This is pretty consistently flat. As I said, this is still a project that we're working on, trying to figure out what exactly is going on. So with that, as I said, we have this other kind of mission. The question is, does it go down to these lowest exoplanets? So the trick is, when you're looking at these lowest, smallest round dwarfs that have had bursts detected from them or any sort of radio emission, the effective temperature is very similar to the most massive exoplanets. So then you do get the question, okay, exoplanets, when you have something close to the 13 Jupiter mass cutoff, that is honestly much more similar to a brown dwarf than it is to Jupiter, right? If you're just thinking about it, or at least it's a reasonable argument to make type thing. I guess we don't know for sure, but as I said, reasonably argument, hopefully. So the idea here was also, as I said, a lot of this, it's kind of tough when you can't tell between the star and the exoplanet. So, but we do have a few exoplanets where, we have them directly imaged, not as many as we want, because it's a very hard thing to do. But so, for example, here on the right, this is 51 Ari is this particular system. And, you can see this is the exoplanet here. Here's the star. It's clearly moving. You can clearly resolve them. So that's very exciting. So what we did with the VLA was we decided to target all the directly imaged exoplanets that are within 50 parsecs. We didn't go further just because the sensitivity starts to really drop once you go beyond 50 parsecs. Cut off 13 Jupiter masses just because we didn't want to have any potential brown dwarfs in our system, and declination over -25 just because, of course, that's how far down the VLA can look. And this resulted in 5 systems with 8 exoplanets. They really need to find more, nearby directly imaged exoplanets for us. And, we can do this a bit more. And the resolution, though, that you get between the star and the exoplanet ranges from 0.4 arc seconds to 102 arc seconds. So that's like, roomy compared to what the VLA can do. So to kind of go into what we did here. So the paper is on the archive for anybody who wants to look at all the gory details. It's actually been accepted. It's not officially in the journal yet. And so what we ended up doing for our survey is we had 3 observations of these exoplanets. This is all at 6 gigahertz, just because we're trying to take maximum advantage of the sensitivity of the VLA over anything else. And we also had some archival observations of 2 exoplanets. They were done at 3 gigahertz, but so, archives, you just take what you get. And then one was pretty short. I'd like to get that longer. I'll talk more about that later. But, anyway, so we had a pretty nice little sample to see if this actually works. No detections, but, the nice thing was we could distinguish between the star emission and the exoplanet emission. So this is pretty neat to see kind of what we can do. So here's 2 of the examples. So GeoPSC and ROS 458. What you can see here is, so if you zoom in, we do have emission. This is all, you're basically just going and using diastrometry to kind of tell exactly where you expect your star to be, and then you can figure out from these directly imaged exoplanet papers where you expect the planet to be. And you could see, okay, there is emission, but there's no emission where the planet is. And it's the same here. ROS 458 is actually a very well studied flare star. But then you can go and you can look where the exoplanet's going to be, and there's no emission there. So this was really nice. It's like, hey, look, you can actually do this. This kind of works. It got even more interesting, trying to rule out emission for 51 Aries. That was actually the one that I showed you earlier with the little movie. And the reason that was kind of interesting was because we actually had a very bright source. It turns out near the position of 51 Aries. So it was about 4 or 5 arc seconds separate. Obviously, it was not in that directly imaged exoplanet optical thing, but that doesn't mean like, it was outside of the optical range of where that image was. So maybe there was an exoplanet just in a very independent orbit. A lot of these brown dwarfs are free floating, not really associating with anything. You don't need a star planet interaction or something like that. It also turns out 51 Area is a 5th magnitude star. If you want to go into, say, the Hubble archives or anything to say, oh, is there a background galaxy there or something like that, that's pretty tough. So all we knew is we had a 90 microJansky source, and it was also varying by a factor of 2 in about 3 hours. So that was, a decent amount if it's just an AGN. Like, it's not impossible, but okay. So what do? The answer is you wait 3 years, and these systems are close enough that they actually will move in the sky relative to any background source. So what we did was roughly 3 years apart, we got another 3-hour observation. And in both cases, you can see this is 51 Area, this is 51 Area B. And we have about 200 milliarc seconds that this would move. And if something is sufficiently bright, the source finding will give you within 200 milliarc seconds of the positional difference or anything like that. And so, this is how much the candidate should have moved. If it was consistent with the system, it did not move. And then, everything else just kind of shifted along. So, okay, that's just a background AGN. That's not an exoplanet, but still, it was pretty interesting to kind of go through this, because I should emphasize, before I started doing this work, everything I've done is like outside the galaxy. So like usually redshifts we talk about. So I was like, oh, this is kind of cool that you can do this. But anyway, going forward, you can also then compare to other ultra-cool dwarfs that have already been detected or not detected to kind of see where we are, what exoplanet range we're in. So this is a little bit of a complicated plot, so I'll talk you through it. So on the bottom x-axis here, we have spectral type, just because a lot of these do not have the exact masses measured. So spectral type is roughly the mass, is kind of how we're doing that. And then this is the luminosity, so adjusting for distance. Everything here that is a square point is the low-level quiescent emission, if you have low-level quiescent emission from that source. And then this, the yellow dot is if you have a flare emission from that. So kind of to say this is the range. The blue triangles are all just upper limits. There are a lot of upper limits in this as well. As I said, it's like a very small population. And then you go down all the way here, we have our exoplanets, which, as I said, were all upper limits. But you can see, as I said, like, this is pretty encouraging. We definitely can see that, okay, we are ruling out a lot of this flaring emission, at least for these exoplanets. So that's pretty good. Of course, as I said, the problem is if you only have a 3-hour observation, we've definitely had this where people looked, just for a few hours at something and then looked again and oh, it's there. So there is still that limitation here.
Oh.
Yeah.
Are they all at the same frequency of 6 gigahertz, or they are at different frequencies?
Most of these are at 6 gigahertz. A handful of them are not, but most of the brown dwarf stuff has been there just because that's been where this has been most successful. As I said, yeah, like if you look at it, usually the peak is somewhere around there as well for these, but there is a slight range here. You can also just compare to the detected ones, tend to have the masses already known. So, we're focusing on just the subset of detected UCDs. You're starting to see, as I said, you're getting a bit of an overlap here. So what is detectable and what isn't. So that's pretty exciting. And you can kind of see, though, that the levels that we're hitting are pretty similar and consistent with what you're seeing from these UCDs. So you can start ruling out a lot of this stuff. And, so the next steps, of course, you're thinking, well, okay, there's, what did I say, 5 of these. I think there's like 1 or 2 that have been discovered since, but this is most directly imaged exoplanets tend to be further away than 50 parsecs. So what can we do next? The first one is we do want to use Meerkat. I haven't heard of a recent call for proposals, unfortunately, with Meerkat. So we're still waiting on that. There's a handful, hopefully, in the Southern Hemisphere. We can also observe things like that. But the more interesting thing, of course, you can do is you can go and get more VLA time to just look at everything out there. And it turns out we convinced them, we've just learned last week that we were successful in this. So we just got 25 hours for a volume limited reconnaissance of exoplanetary systems, because that sounded fancy or something. And we ended up getting 25 hours. And the idea is we're just going to look at all the exoplanets that have not yet been observed by the VLA at 6 gigahertz. So as I said, just taking maximum advantage of that sensitivity that the VLA has, out to 15 parsecs. And we're also going to look at a few beyond. So the way this works is we're just like, okay, I'll show you later. We're looking for a certain sensitivity limit because we know roughly what we need to aim at to rule things out for this natural emission. So as a result, we asked for more time to go out to further distances. Of course, they didn't give us all the time. So we have enough to go out to 15 parsecs and see everything within that, but then we probably still have some for like that require longer observations further out. And we haven't officially decided on the sample yet. And also, so this plot, what you can see is, so this is just the distance of the various things. We also have the masses. We do have everything that's an open orange circle is something that's already been observed in the VLA archives. So none of that, except for maybe like one or two, have ever been published. They're just sitting there. So I assume they're sitting there because they weren't the most exciting, detections in the world or anything, but still we're going to go through, if you have a grad student who's very eager, and analyze all that. And yeah, it's going to give us 45 systems, 75 exoplanets. The question though, of course, is like, as I said, we're limited for directly imaged exoplanets. So just as a proof of concept, most of these were discovered by a radial velocity method. But just because they're very close, if you look at VLBI resolution, all but a handful of them are, if we detected some sort of emission, we're not quite sure, we could follow up with VLBI, see what's going on, something like that. So that is definitely exciting and interesting. So also to go forward here, as I said, so this is, the same plot you saw before, but this is with the new targets and just kind of, so what we were doing, just using the VLA calculator. You can go and say, okay, this is the masses that we are looking at, and this is the logs of the luminosity. Everything within a certain distance, we're only looking for 20 minutes because then we already get down to very, very good sensitivity. 40 minutes for the next sample, and then up to 80 minutes for the furthest out to 15 parsecs ones. And what you can see though is the sensitivity we're getting down to is really going to be the best sensitivity that you're going to get on a survey like this until, of course, the NGVLA, which is also exciting that as of a week or two ago, I can talk about. So, that's pretty cool.
Mm-hmm.
And it's going to be very interesting to see what we see. So I did want to say, because of the group here and everything like that, that SETI is not our primary goal. As I said, we got this because we're looking for this natural radio emission. But obviously, if we're already getting the data, if anybody has any ideas or suggestions on things we can do with it, that might be interesting in a SETI context, because I'm sure, it would be a nice little section in the eventual paper or something. Please share your thoughts with me. I'm very interested in anything somebody might suggest on that front. So just to wrap up here, I hope I convinced you that, the radio detection of exoplanets, natural as well, would still, be very exciting. We would still really open up a huge window to studying exoplanets on all sorts of different interesting topics. Habitability, of course, would also be in there. But also there's things like the interior structure and things that are not really known about exoplanets. That would be pretty cool to probe. Our VLA survey of imaging the nearby directly imaged ones did not yield detections, but it does highlight the need for more of these microJansky sensitivity level surveys with the VLA in order to understand what exactly is going on here. And yeah, so we are also, though, we're pretty encouraged by this. So we're going to go forward, get a more volume limited sample of all the nearby exoplanets. And the time is going to start next spring is the next cycle that we got the time for. So stay tuned. Hopefully we're going to find some more interesting things. So thank you very much.